കുഴപ്പമില്ല. എന്നാല് നമുക്ക്
സംസാരിക്കുമ്പോഴുണ്ടല്ലോ
Good morning, all. This is the 10th lecture of the webinar series Phytech 2020 and the valedictory function of the series. The meeting will start at 10:30 a.m. Today's valedictory function was addressed by Professor M.K. Jairaj, the Honorable Vice Chancellor of University of Calicut. Our resource person for this today's lecture is Dr. Haridas G. Nair. He's is already here. Good morning, sir. So he will talk about India's nuclear programs. So we'll wait for 5 more minutes and then 5-6 minutes and then we'll start the program.
Honorable VC will join now. Welcome, sir. Welcome, sir. Welcome, sir. Good morning, sir.
Good morning.
Good morning. Good morning. Shilu, please.
Good morning, sir. It is Principal Dr. Ena Thomas. Good morning.
Good morning.
Achin, good morning.
Good morning, all of you. A warm welcome to all of you for today's lecture, Phytech series, webinar series 2020, lecture 10 and validatory function. We welcome you all. Our honorable Vice Chancellor is here, and the manager of the local manager of the college, Mata Joseph is here, and Dr. Rena Thomas, the principal of the college, is also here. We welcome you all, and the meeting will start in a minute. We can start the meeting by the welcome address by Dr. R.J. Prakash, the head of the department, physics. Sir, please.
A very warm welcome to the distinguished personalities, all for the last webinar of the Phytech webinar series conducted by the Department of Physics in association with the IQAC of Marthoma College, Chungatara. Respected Professor M.K. Jairaj sir, Honorable VC of University of Calicut, Dr. Haridas G. Nair, Head Health Physics Unit, RR CAT Indoor, Principal Dr. Rena Thomas, College Bursar, Reverend Matai Joseph, IQAC Coordinator Dr. Rajiv Thomas, retired faculty members, Thomas K. George sir, faculty members, participants. We are extremely thankful to the Honorable Vice Chancellor of the University of Calicut, Dr. M.K. Jairaj sir, for spending his valuable time and to address our last webinar of the Phytech webinar series. The physics community is really proud. A physics lover, a very good researcher, and an able administrator to become the Vice Chancellor of Calicut University. Last 2 decades, Professor Jairaj sir's contribution to uplift the physics learning and research are highly appreciated by the entire physics community of Kerala. His constant efforts and encouragement help the students community to reach very higher positions in various organizations throughout the world. I got an opportunity to serve as the Secretary of the Academy of Physics Teachers when he was the president of the organization. With all due respect, a wholehearted welcome to the Honorable Vice Chancellor of University of Calicut, Professor M.K. Jairaj sir. Thank you, sir. Welcome, sir.
Thank you.
Today, we have with us for delivering the final webinar of series, Dr. Haridas G. Nair, Head Health Physics Unit, RR CAT Indoor, under the Department of Atomic Energy. He is a prominent person in his field and very reputed and very reputed works in his credit. Before shifting to RR CAT, he was in BARC and TA for Mumbai. He is the recipient of several awards and more than 50 publications in his credit. Myself and Dr. Haridas G. Nair studied from class 1 onwards to BSc degree in the same school, class and college. I extend a warm welcome to my dear colleague, my dear friend, my dear well-wisher, Dr. Haridas G. Nair, to the webinar series.
Thank you, JP.
I extend a warm welcome to our principal, Dr. Rena Thomas, College Bursar, Reverend Matai Joseph, IQAC Coordinator, Dr. Rajiv Thomas, former head of the department, Professor Thomas K. George sir, Susan Jaco teacher, for their constant support and encouragement. I welcome you all for the Phytech webinar series and express our sincere thanks to all for showing your interest in physics studies. Thank you very much. Shilu.
Yeah. Thank you, sir. I welcome you all the participants present here because you are the encouragement that you have shown. I can see that most of the 50% of the students have attended all the lectures in this Phytech series. We have conducted 10. This is the last one, 10 lectures of the series. So we are going to the function. First, I invite for the presidential address, Dr. Rena Thomas, the principal, Marthoma College, Chungatara, for delivering the principal address. Ma'am. Ma'am, your mic is muted.
Sorry. Is it audible now?
Okay.
Okay, thank you. Good morning, everybody. Honorable Vice Chancellor of our university, Dr. M.K. Jairaj sir. Today's guest speaker, Dr. Haridas Nair. Head of the department, Dr. R.J. Prakash. IQAC coordinator, Dr. Rajiv Thomas. Our Bursar, Reverend Matai Joseph. Former faculty members, the faculty members of our college, participants, well-wishers, and my dear students. I am privileged to be here at the valedictory function of the webinar series organized by the Physics Department of our college, Phytech 2020 webinar series. I appreciate the effort and initiation of Physics Department in organizing such a very relevant webinar series, which is useful to students and other faculty members of their interest. And moreover, we are very happy to have the valuable presence of our Honorable Vice Chancellor, Jairaj sir. Being a physics personality, we wish all the best of your period in the university as the Vice Chancellor will enrich and nourish the science stream. Warm welcome to you, sir, to our community for your valuable presence and being with us. And I'm also happy to have the colleague and friend of JP sir, Dr. Haridas, and we are welcoming him also to our community. Warm welcome, sir. In fact, the physics department have started the first webinar series in our college, and it is the 25th year of the physics department. So I appreciate the head of the department and faculty members and students for their initiative. All the period of this COVID lockdown period, where our various departments have been organizing webinar series, research methodology series, and other contemporary or relevant important topics. And we have converted the pandemic period into a series of learning experiences, and I'm proud of that. And I also thankful to the IQAC for coordinating all the expertise and technical expertise for all the webinar. And I'm happy that this also should enrich the students to go further in science stream. I wish all success to this webinar, and I very happy to address this audience as a principal of Mahatma College. Thank you all. Thank you.
Thank you very much, ma'am, for the constant support and encouragement from your side. That's a reason why we have started such an webinar series. Next, I will invite our Honorable Vice Chancellor, University of Calicut, for the keynote address. Sir, please.
Very good morning to all. Am I audible to all?
Yes.
Yes, sir.
Yes, sir. Yes.
Very good morning to all.
Good morning, sir.
Dr. Reina Thomas, Principal and President of this function. Reverend Father Matai Joseph, College Bursar. Dr. Rajiv Thomas, IQAC Coordinator. My friend, Dr. Jay Prakash, Head of the Department, Physics. Dr. Haridas, the resource person, and faculty members, students and friends. I'm very glad to be part of this webinar series organized by the Department of Physics and IQAC of Mahatma College, Chungatara. The Phytech, the 10-day webinar series organized by IQAC and Department of Physics. The humanities going through a very difficult situation. Today, as this pandemic spreads, we are in the midst of an unprecedented challenge. Indeed, hope is what mankind has relied upon in times of crisis. This too shall pass. We all will overcome this and will be back to normal soon. Under difficult time, teaching community has raised to the occasion. Online classes have become a new norm. though the online classes are new norm, I don't believe that online teaching is not a substitute for direct teaching. But on the difficult times, we have no other way. So, I would advise the teachers also to see that your online classes are reaching all the students. You may be listening to Sam Putroda last week, who was the IT advisor to Prime Minister in 1990s. He was telling that there is a digital divide. We also know that there are more than 30% students who cannot access the online classes on a real time. To make sure that your recorded classes at least to reach the students and they are not left behind. I was listening to some of the counseling meetings which we organize here. The students are undergoing different kinds of pressure. Some of the things which I have not expected because of the lockdown period, they are not in around with the friends and the peers are not there. And some of the girl students feels the pressure of the family that there is no hope in the future. You have to have marriage soon and so on. So they have to leave their expectations and dreams. So they have a mental pressure also there. So all the teachers, you make sure that the students' problems are addressed, or at least you have always a listening ear to them, so they can relax and they can relieve their pressure. Webinar has become now a new norm. There are pros and cons. The advantage is you can attend the webinar from any nook and corner. I see that today's seminar we have more than 80 participants. I am from Tenipalam. I am attending this function because the advancement of technology. The first webinar may be the American Physical Society webinar. The American Physical Society annual meeting was cancelled just 2 days before the conference. That too in March, the beginning of the Corona period. The announcement came when thousands of people were traveling to US to the the seminar site. When they cancelled, the scientists and the academicians posted what they would have presented in the conference, and that started to discussions and formal discussions, and that led to a webinar. From that day onwards, we have outbreak of webinar series. It's a good. We have webinar series, especially to the students under the stress period. They get an exposure to what is going on in the research field as well as in the international scenario. Maybe what we may lose in a webinar is the tea break and the informal discussion during the tea break, and this may lead to lifelong collaborations. But I am sure that the new technology will help us to connect us and make a lifelong collaboration. As I told that online teaching is altogether a different ball game. I believe that there is no substitute for direct teaching. The role of teachers in the present scenario has now changed. Instead of the guru, the authority in their domain knowledge, they have now to act as a facilitator, providing resources, guiding the students how to learn, motivate them to do the self-study. Students also have to change their role. They have to depend on the resources provided by the teachers and have to have a self-learning. Before going to the details, we are also facing some other problems regarding the national education policy. There are controversies, but there are some certain points which we have to take up in the higher education scenario. As the national education policy rightly point out, the universities should be knowledge creation center, and they say that the universities should be multidisciplinary in character. All the subjects should be under one umbrella. It should not be a single domain subject. So they suggest that if you have a multidisciplinary university, they compare with Stanford and MTI. And if you look all the foreign universities and European universities, the strength of students is 20,000, or the tune of 20,000. Okay, and when we compare to the situation in Kerala, each universities we have something like 2,000 to 3,000 students in the campus. So if you have a multidisciplinary university with a character of the Stanford universities, in Kerala we need only one university. So you think about the kind of infrastructure you need, the kind of support you need to the students, and the national education policy is keeping a mum on this. They are not speaking anything about this point. So one of the problem is the higher education becomes so expensive. So who is going to support the students? Whether we are emulating the scenario which is there in the Western or in European universities. But NEP is also keeping nothing. They are not saying nothing about community college, which is prevalent in the US and other European scenario, where you have the access to education even at remote places. So if you have a university setting of this kind, what will happen is the colleges in remote villages, remote areas may have to struggle to keep alive. And NEP points out that the colleges which cannot support themselves, they will wither away. So this become a big problem. What they have envisaged is to have a enrollment ratio almost to 50% by 2030. So instead of enrollment ratio going up, we will see that enrollment ratio dipping down because the education become non-accessible to students who are in the remote areas. One of the points which they have rightly pointed out the areas which India has to concentrate on research. They have clean water and health. That is one of the area. Environment, transportation, energy. And if you look all this area, physics has a prominent role to contribute, whether it is in energy, where it is in transportation, where it is in environment, science or health. Physics students can contribute too much in these areas. I will add one more area, which is the electronics, which is basically semiconductor industry, which we are lacking. We are in far behind. If you look the total contribution of Indian semiconductor industry, it is only 3%. The total semiconductor consumer electronics, if you look, it's a trillions of dollars industry, but the contribution from Indian scenario is only 3%. That too only in the form of passive components. There is no active component devices prepared in India. You look only the devices are capacitors, resistance, like the passive components. There is no industry which deals with very large scale integration. There are only 1 or 2 semiconductor industry under government sector. That's a big problem which we have to address. We are speaking about the machine learning and brain-inspired computing instead of the von Neumann computing. And the next era is going to be the brain-inspired computing, where the physicists can contribute much. So this area has to be addressed. And one of the sector is the energy sector. And India has a mega projects like ITER, International Thermo Energy Reactor, which is 35 countries involved in the ITER project, where you have the tokamak kind thing, where you have the helium nuclear fusion, essentially producing the tritium. So that will produce energy where Q factor is more than 10. Generally, you get an energy output less than the energy input. Here you have the energy output much larger than the energy input. For nuclear fusion, you have to have very high energy, because if you want to combine two lighter elements, lighter nuclei together, it has to overcome the Coulomb repulsion. If you want to remove the Coulomb repulsion, you have to accelerate the nuclei to very high energies. To accelerate or to make it high velocity means you have to provide very high temperature. So you have to produce a temperature of the order of 10,000s of Kelvin, something similar to this process which is happening in sun. So there is a nuclear fusion. So that for a nuclear fusion, you have to give energy input. So the output is more than that you give. So the Q factor they expect as 10. So by 2035, they will be producing a ITER, the thermonuclear reactor in France, where India is one of the participants, and especially physicists can contribute too much into this project. Similarly, we have mega projects like LIGO, Laser Interferometric Gravitational Wave Observatory, which is also in a collaboration with other nations we are building, which will give some insight to the fundamental problems like the black holes and the gravitational waves. We also have mega project like Indian Neutrino Observatory. I just want to show that students that there are much more opportunities in the physics world. When you graduate, you think about going to choosing higher studies and contributing to the scientific scenario. I also advise the students and the faculty members, we also have to train the students from the present scenario is, the present scenario, all think that the purpose of education is to get a job. It is not so. We have to train the students. Instead of job seekers, they should be job providers. They should be start entrepreneurship, and they should be able to contribute to the Indian society. So they should be job providers. And also, as you know, that the success rate of any startup is very, very less, maybe 4%. But we learn from failures, and the experience you get by starting a startup is much, much bigger. And you will be, even the startup is a failure, you will success in your life. And to have a good startup, you have to have an interdisciplinary character. You have an open mind, because if you produce some idea, you need engineers to build it. You need some management people to sell it. So the students of multidisciplinary nature can have to come together, and they have to have a entrepreneurship mentality. And I will advise that each backyard of your home should be a workshop for an entrepreneurship, and you should look as a job provider, not as a job seeker. I'm not prolonging more. I believe that the webinar series must have influenced the students in shaping their future career. And today we have Dr. Haridas speaking about the nuclear energy. I hope that this seminar also will be very good for the students, which is evident from the number of participants I see in the webinar. We have almost 80 students participating in the webinar, which shows that the previous all the webinar series was received success. And I wish all the students the best, and especially the Mathoma College and the Department of Physics all the best in future. And I thanked my friend Dr. Jayaprakash for inviting me to this webinar series. Thank you all.
Thank you, sir. I would like to thank our Honorable Vice Chancellor, Dr. M.K. Jairaj sir, in this occasion because he may not be able to attend the meeting completely. So I would like to thank our Honorable Vice Chancellor. Thank you, sir. Thank you.
Thank you.
Next.
Thank you.
Sir, thank you very much, sir.
Next, I would like to invite our Reverend Mathai Joseph for delivering his talk. Welcome, Achin.
Dr. M.K. Jairaj, the Honorable Vice Chancellor of Calicut University, Principal Dr. Reina Thomas, Dr. Hardas Nair, Dr. Jayaprakash, and all the dear participants in this webinar. I am indeed happy to participate in the valedictory function of this webinar series. I take this opportunity to congratulate Dr. M.K. Jairaj for assuming the leadership of Calicut University as the Vice Chancellor, and I wish him all the best. At a time we all are socially isolated, a positive thing is that various virtual platforms are opening up, are bringing us together, all the people together. And we all understand. Another positive thing related to this is that webinar has become a new norm of the day. For students and academicians, we all know that webinar, it opens up an opportunity to pull together and sharing knowledge in depth. I take this opportunity to congratulate Dr. Jayaprakash and the team under him for organizing this webinar series very successfully. On behalf of the management, I express our deep appreciation for conducting this webinar, and I hope that all who are participating in this webinar series are highly benefited by attending this series of lectures. And I wish all the best to all the participants, and let us be more benefited by these kinds of webinars. Thank you very much.
Thank you, Mathai Joseph Achin, for your good words. Next, I would like to invite our IQAC coordinator, Dr. Rajiv Thomas sir, for delivering a felicitation.
Respected Jairaj sir, Honorable Vice Chancellor of University of Calicut, Haridas sir, today's resource person, Reverend Mathai Joseph, Dr. Reina Thomas, Principal, Dr. R. Jayaprakash, other faculty members, dear participants. I am very happy to participate in this valedictory function of Phytech 2020 organized by the Department of Physics. So they conducted 10 webinar series incorporating very important topic related to physics and very beneficial to the students. I appreciate the Department of Physics, especially Dr. R. Jayaprakash sir, Kishan sir, and Shiv teacher for arranging eminent resource persons for this webinar series and making the resources available to the students. So this webinar series was very beneficial to the students, and I wish all success to the participants and to this webinar. Thank you.
Thank you, Rajiv sir. Next, we have to move on to the lecture 10 of the Phytech webinar series in India's nuclear programs by Dr. Haridas G. Nair. For this, I would like to invite Haridas sir to our webinar. Welcome, sir.
Hello. Are you able to hear
Yes,
me?
sir. Yes, yes, sir.
Yeah. Very good morning to all of you. Especially, I'm very privileged to hear from Professor M.K. Jairaj, Honorable Vice Chancellor of Calicut University, because when I was hearing the keynote address by him, I felt that he has almost touched upon the challenges what we are going to face and what we are facing presently, and what are the things which we require for uh, moving ahead to meet our challenges. So I am also very honored to hear from Professor Jairaj. And then the next thing is about Dr. Jaiprakash, as he has mentioned in the beginning, in the introduction, that yeah, I am his classmate from first standard onwards till BSc. So, in fact, Dr. Jaiprakash was asking me to deliver a talk since long, but due to many reasons, I was not able to come to Sungatara Marthoma College and deliver the talk. But now this COVID pandemic has created a lot of opportunities, and due to which I am able to give the lecture from indoor. I am also very thankful to Jaiprakash for inviting me for delivering this lecture, and also to other team members of the Department of Physics, Marthoma College, for organizing such a wonderful series of webinars by eminent personalities across our country. Without taking much time, I would like to go to the presentation. I will be briefly talking about the nuclear energy programs. Hello. Hello.
Sir, it's
Are you
audible.
able to? Okay. Are you able to speak?
Audible, and presentation is clear.
Presentation is also very clear. So I'll be briefly talking about India's nuclear power program. In fact, in the beginning, I was trying to talk about accelerators, where I am deeply involved. But then I thought that it may be better if we talk about India's nuclear power program, as Professor Jairaj also pointed out in the beginning, that the societal applications, or the application which are beneficial to the human kind, is the thing where we have to give a lot of importance. So I thought that it is maybe interesting or fascinating to share the knowledge of about the India's nuclear power program. Now, when we talk about the nuclear power program, this is the outline of the talk. That is, first is I'll just briefly talk about the nuclear fission. In fact, as many students may be knowing about nuclear fission and all, but I thought that before going to India's three-stage nuclear program, it is worth discussing about the physics, a little bit of physics behind that. So I will be talking about nuclear fission, then what is a nuclear reactor, and then come to India's 3-stage nuclear program, and then somewhat advanced technology of accelerator driven subcritical reactor where India is pursuing, and safety issues and summary. So now the discovery of nuclear fission, as you know that it has happened in the year 1938. And you can see that there are two eminent personalities. One is Professor Otto Hahn and Fritz Strassmann, which may be very familiar. These are the Hahn and Strassmann. It is very famous terminology, the phrase that they are the two German chemists who worked on nuclear fission. And for this work, Hahn got the Nobel Prize in Chemistry in the year 1944. This is the model of the experimental setup they have used. There is not much complicated system and all those things. But surprisingly, I have put another lady's photograph here. This is Meitner. See, you know, I have written here, discovered nuclear fission unexpected. See, most of the discoveries are unexpected. Why I mention that it is unexpected? Because as we know that in 1932, Chadwick discovered neutron when he was bombarding energetic alpha particles on beryllium. He found that some particle has emitted which is of no charge, which is neither deflected by the electric field or the magnetic field, but it has some mass. So that is how neutron was discovered. But later on, many scientists started experimenting with neutron by bombarding neutron with many heavy elements and try to look for different still higher elements. So now this lady Meitner was a colleague of, or you can say that she was very fascinated in doing research, and she came to Professor Hahn for doing experiments and all those things, and they were carrying out many experiments together, bombarding particles with different elements, etc., etc. But later on, due to some ethical issue, she has to leave. She's a Swedish physicist, and she has to leave Germany. But then Professor Hahn continued the experiment by bombarding neutrons with uranium. So when he started bombarding neutron with uranium, or say rather the other way around, uranium with neutron, he found that some barium isotope. He found that some barium isotope was formed. In fact, when I said unexpected, see, they were looking for something else. They thought that when uranium is bombarded with a neutron, some other heavy elements will be formed. But on the contrary, they found that small fragments were formed. But he was not able to explain. This Otto Hahn was not able to explain. He wrote to Meitner telling that such a thing has happened. I do not know what is the reason and all. He was also puzzled. But this lady is the one who went into the details of the process, and along with one of her colleagues, one of the physicists, during a morning walk, they discussed and found that it may be due to fragmentation of the heavy uranium nucleus into small pieces, just like a liquid drop. Suppose if you have a liquid drop, spherical drop, if you just bombard with some, or if you disturb it, it may break up. So a similar analogy that time Professor Gamow has pointed out the liquid drop suggestion long back, a Russian physicist. So she only gave the clue that it may be because of the fission. But somehow, tragically, it is very sad to hear that this lady was not rewarded for this. But Hahn got the Nobel Prize in Chemistry. Anyway, that is very interesting. If you look at the history of any discovery, it's very fascinating facts you can find out. Now, what is nuclear fission, basically? See, you have a heavy element, which we call it as the target nucleus. And when you allow to bombard with a neutron, it produces fission fragments. You can see 2 fission fragments, and along with 3 neutrons will come. 2 to 3 neutrons will come out. Now, it is why this fragmentation is happening. Has been explained with the help of the liquid drop model, which many of you are aware that This is a spherical stable nucleus. When you give some excitation energy, it will start oscillating, and then oscillations will keep on building up, and there will be a waste formed, and finally it will split into two fragments. And now the energy which is released during this process, this is very important. The entire nuclear energy program across the world, not only in India, across the world, is based on this process where the energy released is given by delta mc square. So that means if you look at if you compare the mass of the products which is formed and the original mass of the system, there is neutron plus this target nucleus and the particles, the fragments which is released. If you take the difference of they found that the sum of the products have some deficit in some mass, and that deficit in mass is contributing, because Einstein's mass energy relationship, any mass is associated with the energy mc square. So we get the velocity of the light square multiplied by the delta m. You will get something around 200 MeV per fission. That means if uranium-235 nucleus is split into two by the fission process, the energy release is around 200 MeV per fission. It's a very large amount of energy. Now, see, when you look at the fission yield curve, that means whatever fission is taking place, the fragments, these are the yield of the fragments. See, in the case of a uranium-235 nucleus, it can get split into 40 ways. Barium and krypton is one, but there are many other ways by which it can undergo fission. So each fragment has around 2 to 3 total products. That means around 200 to around 200 radioisotopes are generated in a reactor core. We will later on discuss what is this reactor core, what is the fuel, etc., etc. Now, as we've discussed about the fundamental process fission, but to sustain, to maintain a steady power, because when electricity means we want to have a continuous supply of power without any interruption. So that is obtained with the help of a chain reaction. With the help of a chain reaction is what? The first generation is that one neutron interacting with the heavy nucleus, then two neutrons are generated. These two neutrons are again creating further fission. Again, you are getting further neutrons which will continue to generate fission process. So we call it as the first generation. First generation, there is 2 raised to 1 neutron, the 2 neutrons. The second generation, there is 2 raised to 2, 4 neutrons. Third generation is 2 raised to 3, 8 neutrons. So this chain reaction will keep on going. So now, see, if 10 to the power of 10 fissions are take place per second, that means if you take from 200 to 200 MeV per fission, and if we just calculate, you can find that a simple calculation, you can get that 1 watt of power is corresponding to around 3 × 10 to the power of 10 fissions. And now I have put a figure on the right side to tell you what is the potential of this chain reaction. Suppose if you allow this chain reaction to keep continuing, if you keep on second generation, third generation, fourth generation, nth generation, keep on allowing to proceed like this, then it will result in a huge amount of energy which is released, which we call it as a nuclear bomb. So this is a typical figure which I have taken to show you that how a nuclear bomb is exploded. So now, but we don't want nuclear bomb. We want nuclear power. Now, when you want to have a nuclear power, then you need to have something which is steady. So how the steadiness is obtained? There is a factor called K factor. K factor means, as I explained in the previous slide, that the neutrons keep on increasing in the number because of the fission process. But if you are able to maintain the number of neutrons from one generation to the neutron from the previous generation, if we maintain the K factor is equal to 1, that means there is a steady multiplication. That is, the multiplication of neutron multiplication is 1. In that case, we call it as a chain reaction, we call it as a critical chain reaction. You will get a steady power. But then suppose if K is greater than 1, that means you are not able to maintain K is equal to 1, or this ratio, neutron from one generation to the previous generation, if you are not able to maintain 1, then it becomes a supercritical reactor, or which we call it as a nuclear bomb. And if K is greater than 1, less than 1, then we call it as a subcritical reactor. Subcritical reactor is supposed to be a safe reactor, which I will tell in my last part of the talk. Now, of course, we simply mentioned about the K as the ratio of the neutron from the present generation to the previous generation, but there are many factors which we call it as a 4-factor formula, which is eta epsilon PF, where I mean, anyway, you all can get from your books and all. Because for a infinite system, you know that the number of eta is the number of neutrons produced per neutron absorbed. Because not necessarily that a neutron absorbed in the system may produce neutron. So there is a factor which is accounting for that. This is eta. Then you have a fast fission factor. See, as I showed a slide about uranium-235. Uranium-235, when it undergoes fission, it is undergoing fission with a slow neutron, that is a thermal neutron. But you have a fast fission factor also, because all these processes are described with the help of a term called cross-section. The cross-section, as Dr. Jairaj also was mentioning about the helium fusion and etc., and hydrogen fusion, ITER, etc. So they are all determined by a parameter called cross-section. So you have a cross-section for all energies, though thermal neutron have the highest cross-section. So what is the fast fission factor? When there is a resonance escape probability, that means the neutrons which are generated in the reactor system, see, it may escape also. So what is that probability? Then the thermal utilization factor, that is the fraction of thermal neutrons absorbed. All thermal neutrons need not be, because they are all probabilistic phenomena. So taking all this factor, one will theoretically find out what is the K factor of the reactor. Now, let us look at, slowly we are coming to the nuclear part. Let us see what is how a nuclear reactor look like. In fact, I am very sure that all the students know that how electricity is generated. Because a very simple example, if you take that, see, we all use cycle. I mean, I don't know, nowadays cycling is between our olden days when we go to college, school and etc. We go by cycle only. And in cycle, see, there is a dynamo which is already, some people used to keep dynamo. So when you keep on the dynamo, what happens that the coil which is associated with the dynamo, it rotates as the wheel rotates, and electricity is generated. Exactly in the same way, here you can see a turbine, which is like the dynamo of your cycle. If you allow this thing to rotate, then electricity will be generated. So this part is common for all the power generating system. You have a turbine, and then you have a generator from where the electricity is generated, and it is given to the grid for utilization. But now the first part is the one which changes. See, we have nuclear power, we have thermal power, we have hydro, we have this fossil fuel. So many type of, we will discuss later on. But this is the part where we are Department of Atomic Energy is focusing on. That is the nuclear part. Now you have I will show in the next slide a little bit in detail. So this red portion, what you are seeing is the nuclear fuel, and this is the reactor core, and this is the what you call the reactor vessel through which you can see the cooling water is being supplied, and the cooling water which goes inside, it will exchange the energy, or it will take away the energy from the nuclear fission process, and it will come out, and this is the highly hot, and that heat energy will be transferred to a steam generator. Here the steam will be generated at high pressure, and the steam will then at this high pressure it will come, and then it will allow the turbine to rotate. So this is what exactly it happens. But then the cooling water will have to be the hot water has to be taken out, then it has to be cooled, and then again it has to be fed to the. So it is a closed cycle. And you can see a containment which is outside. This is called the containment structure. People are very much worried about the nuclear reactor safety. I will touch upon that aspect maybe later on. So this is the containment structure where the entire system will be contained. So you have the reactor core, Calentria vessel, you have the steam generator, and the condenser system and the turbine. See, these are the some of the main elements of this thing. So somewhat in detail, I have shown here. This is the reactor core, where you can see the core or driver which is kept. That means the fuel is placed here, uranium-235 or other type of fuels also I will discuss. Then you can see some control rods here. So why this control? What is the significance of this control rod? As I said in one of my previous slides, that if you allow the chain reaction, if you allow the chain reaction to be controlled, that is controlled nuclear chain reaction, which is used in a reactor. But suppose if you don't control, then it will result in a bomb, as I explained, because of the high temperature. It will, reactor core, everything will get melted and it will come out. You may be remembering that a very famous accident took place in Chernobyl in Russia, where this reactor core, this portion got melted because of the over temperature or the failure of the cooling system, and all the radioactivity came out. So this control rod, the function of the control rod is to control, the name itself is telling that control, it is a control rod. It controls the nuclear chain reaction. And how does it control the nuclear chain reaction? You can, nuclear fission is caused by neutrons. So if you are able to absorb the neutron somehow, then you will not allow the fission to take place. So this is by inserting the control rods. So for example, there are special materials called cadmium. Cadmium has got a very high absorption cross-section for neutrons, especially thermal neutrons. So if a thermal neutron is coming, and on the way, if you insert a control rod, the thermal neutron will be absorbed. So further fission will not take place. So there are many safety systems where this nuclear chain reaction is controlled. This is one mechanism. And now let us come to from this fundamental, let us come to the energy sources what we have. There are mainly two types. One is the conventional, or we call it as the non-renewable. They are oil, coal, natural gas, and nuclear. And the non-conventional is like hydro, geothermal, solar, wind. So now we get energy from all these sources. So let us see what is the world scenario in the electricity generation. See, you can see that in across the world, on an average, 42% is from the coal, and you can see around 14% is nuclear, and 21% is natural gas and renewable. That is this hydro, then solar, wind, all these things put together, you have 18%. So this is the world scenario. And let us see the countries, or sorry, I will go to the India. So in India, so what is the scenario? So when we compare, see, we have around 63% from the thermal. We are depending heavily on thermal reactors. That is around 63%. But in the world, it is only 42%. Then we have renewable around 18%. And that is in India, we have 23%, world 23%. And let us come to the nuclear part. Nuclear part, we have only 2%, around 6,780 megawatt electrical is the power. And the world, it is 14%, we are having only 2%. Now there are, I showed my previous slide, see the number of nuclear reactors in major countries. I only listed some of the countries where they have more than 10 reactors. Starting from Canada and USA, the highest number of nuclear reactors USA has, around 90, around 100 reactors they have. but the share is only 19.3%. But the highest nuclear share is for France, which is slightly above 70%. And India, we stand at around, we have around 22 nuclear reactors where we stand at only 2.1%. Now I am just giving you sharing you an important slide where I compare what are the energy resources we have. I have listed coal, natural uranium, depleted uranium, thorium. Because see, when we talk about the conventional energy resources, see, there is some limitation. Conventional energy sources means, see, for example, coal. The deposit of coal, if you keep on consuming coal for several hundreds of years, definitely the capacities or the resource is going to be exhausted. Similarly, natural uranium or the depleted uranium, all these things, if you presently we are using these. So if you look at the number of years by which we can generate the number of years by which we can generate the energy, coal, we have only 81 years. Natural uranium, presently we are depending upon natural uranium, which is only 35 years left. Depleted uranium, it is 65 years left. But if you look at the thorium, we have around 225,000 tons of thorium in our country, where we can easily pull on up to around 500 years. This is a very important, that's why I have put it in green. Look at the next slide. The United Nations Geological Survey 2011, they have quantified the thorium across the world, and you can see that India around 9,63,000 tons. And if you keep on looking at the other countries, and if you take the world total, see, it is around 19,13,000, and India has got around almost 50% of the total reserve. This is a very, very interesting figure and very motivating figure for India, that such a large reserve, the total world reserve, out of the 50% fuel thorium we have. So why don't we utilize that? That is the whole process of India's nuclear program, third nuclear program, three-stage nuclear program. Now let us come to the reactions which are more important in the nuclear program, because that will help in the understanding the further slides. The first reaction, anyway, most of the people may be knowing that this is the fission reaction, that if a uranium-235 undergoes fission, it will produce fission fragments, strontium, xenon, one pair of fission fragment I have shown, by neutron plus energy. But then you look at the uranium which is available in the nature. There are two types. One is uranium-238, which is around 99.7%, and we have uranium-235, which is only 0.3%. And you may wonder that all the nuclear reaction or all the nuclear fission process or the nuclear fission reactors which are operated in our country is based on this 0.3% uranium-235 which is available. And now when you call it depleted uranium means the uranium which is depleted of U-235. U-235 is a fissile fuel. See, I'll introduce two terms here. One is the fertile fuel and another is the fissile fuel. When you call a fuel fissile fuel, that means that fuel is easily fissionable. They are called a fissile fuel. Three examples I have put it: uranium-235, then uranium-233, and plutonium-239. You can easily make it fission. But there are two other isotopes which I have listed here: 238, uranium-238, and thorium-232. They are not fissile, but they are fertile fuels. When you call fertile fuels, The meaning is that these fertile fuels will not undergo fission very easily with thermal neutrons, but it can be made fissile. It can be made fissile, so we call it as a fertile fuel. Now, how can you make a fertile fuel to a fissile fuel? Look at this reaction. We call it as a breeding reaction. The breeding reaction, as I said, that uranium-238 is a fertile fuel. If this uranium-238, if you bombard with a neutron, it will just convert it to uranium-239, and then it will undergo a beta decay, where the atomic number will change from 92 to 93, and Neptunium-239 will be formed, which will be converted to, again with a beta decay, to plutonium-239. So plutonium-239 is a fissile fuel. So that means the fertile fuel you have converted into a fissile fuel. Similarly, another important reaction where this thorium-232 is converted to a fissile fuel is through this reaction. Thorium-232, allowed to bombard with a neutron, it gets converted into thorium-233, and then Pa-239 with the help of a beta decay, it gets converted to uranium-233, which is again a fissile fuel. So this reaction is very important. This first reaction is used in the first stage nuclear program, and the second and the third breeding reaction which I have listed is the reaction which is deployed or used in the generation of the second and the third stage nuclear power generation. I think you are able to, grasp what I am telling. Am I correct?
Yes, sir.
Good. Okay, fine. So now let us see what is the third stage nuclear program. See, the first we have, let us say PSW. This is the first stage, where the uranium, the fuel used is natural uranium. As I said, that natural uranium contains 238 and 235, where 235 is what we used for the generation of nuclear power in a pressurized heavy water reactor. So the first stage is the pressurized heavy water reactor. Now, in that reactor, the electricity will be generated 30 years, etc. But then from that reactor, you know that some plutonium will be generated through the breeding reaction. See, as uranium contains 238 and 235, 235 is used for electricity generation, but 238, which is 99.7%, it will just convert it to plutonium due to the breeding reaction. And that plutonium which is generated in the first stage will be used in the second stage. So you see, the stage 2 is the plutonium fueled, we call it as the fast breeder reactor. That is, fast neutrons are breeding for conversion of the fertile to a fissile fuel. So here, second stage plutonium will be used, electricity will be generated. But one interesting thing is that in the second stage, you use thorium also along with plutonium as a blanket. See, blanket means, see, when you, see, for example, during the winter season, if you sleep, you will cover your body with a blanket. Similarly, plutonium fuel will be, from the first stage, will be covered with a blanket of thorium. Why? It is covered because when it undergoes interaction with neutrons, the thorium will get breeded, or it will get converted to uranium-233, which will be a fuel for the third stage. Right? You see the beauty of the process. On the first stage, you get electricity from 235, and you get as a byproduct, which is plutonium-238, 239, which is a fissile fuel, will be used in the second stage, where thorium will be used as a blanket, and you will get uranium-233 from the thorium breeding reaction. From plutonium, you will generate electricity, and the byproduct uranium-233 will be used in the third stage, where we call it as the U-233 fueled breeder reactors. And here you can produce, you can put more thorium along with uranium-233. Thorium blanket again you can put here, again it is put here to produce more U-233, which will be again put as a fuel in this reactor. And finally you will get electricity, which you can get for almost the estimation. This is the estimation based on the thorium reserve and the reserves and the calculation. It is estimated that it can give rise to a sustainable energy for 500 years. And I am very proud to say that in India, under the Department of Atomic Energy, Government of India, Kalpakkam, we have a center at Kalpakkam in Tamil Nadu, where you will be able to find all these three types of reactors. That is the only place in the world where all the three type of reactors are operating. Of course, now presently we are in the first stage. Second stage, these fast breeder reactors are being built. A 500 megawatt fast reactor is being built at Kalpakkam, and this thorium based, again, the prototype, the reactions, the modeling, the simulations, all these things are in progress. Now, so this was just for information's sake. See, these are the nuclear power plants operated in India. Now, see, you can look at the 1969 is the first nuclear power plant at Tarapur Atomic Power Station, Maharashtra, which is set up with the collaboration of General Electric Company, GEC, USA. Subsequently, see, that was a boiling water reactor. The problem with the boiling water reactor is that the fuel is not natural uranium. We have got a lot of natural uranium, but in the boiling water reactor, the fuel used is enriched uranium. What do you mean by enrichment? Enrichment, the process of enrichment is that, as I said, that only 0.3% is uranium-235 in the natural resources. Suppose if you increase that 0.3% to, let us say, 5%, 10%, etc., by some mechanism, we call it as enrichment. We have a plant at Mysore, RMP, we call it the rare metal plant, where this fuel enrichment process takes place. Many information I will not be able to share because of the nature of secrecy, because this is related with something related with the nuclear weapon, etc., etc. So I'll not be able to disclose all those details. So boiling water. So the fuel was imported from USA and all. So there was some limitation, because of the nuclear non-proliferation treaty, etc. There are some IAEA safeguard. So there was some limitation. So we realized this and we switched over to PSW, that is pressurized heavy water reactor. All the reactors which are operating now, around 20 reactors, 18 reactors, they are pressurized heavy water reactor. Pressurized heavy water, the advantage is that you can use natural uranium. You don't have to do any further enrichment or complicated process. Only thing is that you have to fabricate the fuel. Why pressurized heavy water is used? What is the role of this heavy water? Why not light water? That is a fundamental question which I think I would share that. See, this if you use and this pressurized heavy water is a very expensive one, which is more expensive than gold, because from seawater you have to extract. We have a heavy water board where this heavy water is extracted. It is very precious. But the advantage is that if you use normal water, these neutrons, you might have studied about the interaction of radiation with matter, where gamma rays, X-rays, neutrons, how do they interact with matter? If you recollect that when neutrons interact with matter, always there is a tendency that or the cross section for maximum interaction with the low atomic number materials, right? Whereas X-ray is totally different. X-rays has an interaction cross section with heavy materials, like if you remember photoelectric effect, Compton scattering, etc. They are heavily atomic number dependent. But in the case of neutron interaction, it interacts more dominantly with low atomic number material. So if you use light water, this neutron will be easily absorbed by the water, and it will not be available for the fission process. So in order to avoid the absorption of neutrons, you use pressurized heavy water. Heavy water is its atomic, mass is 2, hydrogen it is 1. So since the mass is 2, the absorption will be less, so that thermal neutrons will be available for the fission process. That is how pressurized heavy water is used. And why it is pressurized? As you know that, because each and everything has got a fundamental physics behind that. See, if you pressurize a system, see, for example, water, if you pressurize, the boiling point increases. It will not boil very easily. So more heat you can extract, because this pressurized heavy water, it is used as a moderator to moderate the fast neutrons, because that I think I missed that when during the fission process, see, you see the beauty. The fission takes place with thermal neutrons. Uranium-235, when it undergoes fission, it is with fast thermal neutron. But during the fission, fast neutrons are released. The 2 neutrons or the 3 neutrons which are released are fast neutrons. So they are to be slowed down. They have to be brought down to thermal energy or thermal neutrons, so that it will create further fission. Otherwise, fission will not take place. You will not get energy. So that moderation, it is called, that process of slowing down of energy within the reactor system is called as moderation. And the moderation is done with this pressurized heavy water. Plus, pressurized heavy water has got another role to carry away the decay heat or the heat or the fission heat. The energy, ultimately the energy which is released during the fission process, you have to carry it to the steam generator. I showed in one of the slides, the steam generator. So when you pressurize the water, the boiling point increases and it can capture more energy without boiling, and it can transfer to the steam generator. That's why pressurized heavy water reactor is used. And now we have the 2 latest reactors which are added at Kudankulam, which is a 1000 megawatt reactor, which is using enriched uranium with a light water. In enriched uranium, you can use light water, because the fuel itself is enriched. So even if some neutron is absorbed in water, doesn't matter. So you can afford to have hydrogen or the light water for an enriched uranium fuel. And now there are some projects which are already under construction also, which can generate around 7 units, around 5,300 megawatt electrical. They are going to be operated very soon. And of course, there are around 4 clusters of nuclear reactors are also identified at many places in India, like in Jitapur, Maharashtra. Around 6 reactors are planned. In Gujarat, Chayamiti, Vardi, Gujarat, around 6 reactors. And in Andhra Pradesh, Kovada, around 6 reactors. And in West Bengal, Hiripur, 6 reactors. So huge cluster of nuclear reactors are going to come. Government of India has given in principle approval for this. But of course, there are many stages which one has to. The whole idea is that the 2% which we are having, the nuclear share, we have to increase that percentage to significant amount, so that we can progress as a developed country. As you know, that a developed country has got the per capita electric consumption very high. If you compare with US, Canada, etc., we are far behind. So this is the idea of this program. And now, see, when we talk about this nuclear program, there is a common terminology which comes with the nuclear fuel cycle. And nuclear fuel cycle means it's a cycle. That means it starts from the mineral exploration. See, for example, where is the mineral? We do not know. It is beneath the Earth's crust. So we have to find out where the mineral is there. That we call it as the mineral exploration. We have got under the Department of Atomic Energy, we have got a division called Atomic Minerals Division. They keep on exploring by aerial survey. They find out is there any chance of uranium deposits at places, etc. Then once you explore it, then you have to mine. That is the uranium mining process. Then you have a milling, that is treatment of the, it is what we call it as yellow cake. We treatment of that this thing, chemical process, and then finally you have to fabricate a fuel which is suitable for putting in a reactor for the fission reaction, and then heavy water production for moderation and cooling of the fast neutrons, and then the reactor operation, that is electricity generation. Till this part we have discussed, but now when you come to the next stage, that is the reprocessing of spent fuel, is a very difficult process where, you know, in a reactor, when some fuel is loaded and it operates for, say, for example, many years, not necessarily all the fuel is consumed. There will be some portion of the fuel which is always left unused. We call it as the unspent fuel, or the spent portion. There is some unspent portion is there, and the spent portion. So we have to separate the spent and the unspent part, which we call it as the reprocessing of the spent fuel. So where the unspent part is separated and it is again used in the reactor, and the spent part, that there is a radioactive waste, and you have to do the radioactive waste management. There is safe storage of the long-lived radioactive waste. The entire process is called the nuclear fuel cycle, and we should be proud to say, as Indians, that India is one among the 5 countries having the capability of entire nuclear fuel cycle. America, France, Korea, and India. So we should be very proud of this. So this is the picture of the nuclear fuel cycle process. I mean, exploration, then mining, then conversion. If you want to enrich it, fuel fabrication. So we have fuel fabrication facility at Hyderabad, that is nuclear fuel complex, where all the nuclear fuels are fabricated, and it is sent to the reactors. Then reactors, then spent fuel storage, then reprocessing, then the waste storage, then again to the reactors. So then you have, of course, there are a lot of, actually it's very simple to say, but behind this enormous amount of research and development has to be carried out, and several equipments are to be, high-tech equipments are to be manufactured for establishing the entire process. Now, after coming to the third stage nuclear program, I will slightly switch over to the somewhat detailed or advanced technology called the accelerator driven subcritical system, which is called it as ADSS. Now, so till now we were discussing about the critical reactors where the K effective was 1, but now we will be discussing the subcritical reactor where K is less than 1. Now, what is so advantageous, or what is the motivating factor behind this ADSS system? One is, of course, to produce energy. Second is to have efficient use of thorium resources. As you know that we have a large amount of thorium, so how to utilize efficiently. Then another important application of this accelerator driven subcritical system is the transmutation of high level long-lived radioactive waste and minor actinides. See, in a reactor, when it is operated, you know, many fission products are released, and many of them are highly long-lived. Their half-life is very, very high. I think you all know what is the half-life of this thing. That there are hundreds and millions of years half-life, but how do you store that? If you store it, then you have a problem. There is always a risk. So now the world over, a thought has been created that how to convert this long-lived radioactive waste into short-lived radioactive waste for this ADSS system is very useful. Now let us see how it is advantageous if you use the thorium-uranium cycle. See, for example, uranium-plutonium cycle. See the minor actinides. See, I have listed some of the minor actinides: neptunium, americium, 241, 242, 243, Then you have curium 242, 244. You see, the half-life is 10 to the power of 6 years, 432 years, 7,000 years, 163 years, something like that. Now if per kilowatt, see per gigawatt electrical of year operation, the kilogram of this or the quantity of this minor actinide that is generated is something like this, 4.64, 0.071, etc. But if you go to the thorium uranium cycle, you see it is negligible. This high half-life minor actinide generation is negligible, nothing. So this is one of the advantage. We have a hell of problems in storing this radioactive waste. So this is a major advantage. So ADSS system will help in converting this minor actinide or long-lived radioactive waste into short-lived radioactive waste, where you have a ease of handling radioactive waste. Now, what is the basic idea of an accelerator-driven subcritical system? Critical reactor I have already told. Now, in a subcritical reactor, the external supply of neutrons are to be given for maintaining the reactor at a constant power. Now, this is provided by an accelerator. So, this is, you can say that it is a marriage between an accelerator and a nuclear reactor. See, you know that when fission process, you will get on an average 2 neutrons per fission. But if you allow a high energy proton beam of 1 GeV energy, then you will be able to generate large number of neutrons. See, as I said that in fission 2 neutrons, but if 1 GeV, one proton is interacting with a heavy target like lead or uranium, you can get around 20 to 40 neutrons per proton. So these neutrons can be used for maintaining a subcritical reactor. See, the schematic diagram of a subcritical reactor looks like this. See, this green portion is the target, which we call it as a spallation target, where a proton beam, high energy proton beam from an accelerator, either it can be a linear accelerator or it can be a cyclotron type of accelerator, where this particle proton is accelerated and it is extracted and it is allowed to put it on a target, spallation target, either uranium or lead, heavy elements, where a lot of neutrons will be generated in all directions. And you can see that surrounding the spallation target, this is the subcritical reactor, where you have a uranium cycle can be achieved by putting a reactor. This is the reactor core. You can say the reactor core is here. And then you extract the energy from here. Of course, here also the thing is the coolant, all those things will be there. You have to extract the energy, and this energy will be used for to the grid for the power supply for the domestic use, and a fraction of the energy will be fed back as a feedback loop to the accelerator system for running the accelerator. So it's a closed loop. So this is the schematic of the ADSS system. Now, a conceptual design, it looks something like this. You have the accelerator, proton beam, you are beaming to the spallation target here. This is a picture from a simulation which is carried out. You can see this on the right side, what you see, the brick red color, this is the subcritical fuel. That is the thorium uranium cycle. And this is the spallation reaction taking place. Neutrons are released here, the breeding and all the other system, heat exchanger, everything will be inside this reactor, subcritical reactor. And you can see, as I said, that large number of neutrons will be generated by this spallation process. Now, when I said 1 GeV, you may ask that why 1 GeV? Why not 2 GeV or why not 500 MeV? See, you look at this curve. This curve says that with respect to the proton energy, the neutron yield is given here, right? So now you can see one blue curve, which is that the neutron per incident proton, it keeps on increasing as the energy of the proton is increased. But as the neutrons per this is per watt of the proton beam, if you plot, you can find that at around 1 GeV or so, around 1000 MeV, it saturates. Beyond that, it is almost constant. So they have fixed that 1 GeV proton is the, because see, when you developing a proton accelerator is a very difficult task. It is not an easy. A lot of high technology inputs are required, like superconducting technology, magnets, electromagnets, radio frequency technology, then ultra high vacuum systems, then detailed physics design calculations. So this is one of the aspects. How do we fix up the energy? It is coming from this curve. Now, India has developed a scheme based on this concept of ADSS. The scheme is like this. This is the end portion, that is the subcritical reactor. The scheme is like this. We have a initial ion source, that is proton ion source of 50 keV. Then you have a small accelerator, which is a radio frequency quadrupole, which gives an output of 3 MeV. It will is put it into a LINAC, that is drift tube LINAC. It accelerates the proton to 20 MeV. From there, you can use either a normal conducting drift tube LINAC or a superconducting drift tube LINAC. This is a phase 2. And then it generates 200 MeV. Then it goes to a superconducting linear accelerator where 1 GeV proton will be generated. And then it is beamed to the subcritical reactor system. So this is divided in 3 phases. You can see this is the first phase, this is the second phase, and this is the third phase. Now we are presently at this phase. Almost this portion, this phase 1, we have almost achieved, you can say, or nearing completion, and we have to go a long way, because it's not going to be achieved in 5 years or 10 years or 15 years. Maybe it may take a few decades for this, but this is a long roadmap for the project, but it's very vigorously being pursued. Now, the previous slides, whatever I have shown, the schematic diagram, the components, but these are some of the pictures where the development which took place at the Bhabha Atomic Research Center. You can see the ion source of 50 milliampere proton beam. I mean, maybe by looking at this, you may not be able to understand a bit, in detail. Basically, ion source means you have a hydrogen gas. The hydrogen gas, you have to either generate a plasma. In plasma, you will get electrons will be stripped off, and you will get H plus ions, where you can extract the charged H minus or H plus ion by applying appropriate accelerating potential. This is basic fundamental of an ion source. So that is the starting point. From there, you have a low energy beam transport. You have to transport the beam through a vacuum pipe where the beam has to be guided with the help of magnets, etc. And then you have a radio frequency quadrupole where beam will be further accelerated, and then again you have the magnet to analyze what is the beam which is coming, what is the charge. So these type of developments have already taken place, and now the whatever things we have discussed, ultimately the ADSS has to be tested. The testing part also has to be done. You know, in BRC, a facility has been created, which we call it as a prototype ADS facility, because 1 GeV accelerator, all those things will come on a later on stage. But before that, you have to study the neutronics of the ADS system. So at Purnima Labs in BRC, based on the DT and DD reaction, because these two reactions will generate neutrons, and those neutrons are used for a subcritical fission process. The basic idea of this setup is to have measurement of neutron flux distribution, spectra, then the total fission power, source multiplication, degree of subcriticality, how much it is, whether it is 0.8, 0.9, 0.98, all these studies. So we called it as the Brahma, that is beryllium oxide reflected and HDPE moderated multiplying assembly. So this is the subcritical reactor system, which is a prototype which is made using a DD-DT reaction, and the K effective, which we have described in one of my previous slide, for a critical reactor it is 1. So here we have achieved 0.8. So this type of studies are also being carried out. Now, of course, this is a list of the ADS project across the world. But now I tell you, across the world, this ADSS project is used mainly for the transmutation of long-lived radioactive waste to a short-lived radioactive waste. But India has both the purpose to convert the nuclear waste, long-lived waste to short-lived. At the same time, we have to utilize the thorium for power generation also. Now, I think I have taken slightly more time, but I'll finish maybe within 1 or 2 slides. There are some safety issues. As you know that there are many accidents have taken place in the world. Not many, but few accidents have taken place. One of the most important is the Chernobyl nuclear reactor accident in Russia. Then we have 3 Mile Island in USA. And recently, in the year 2011, at Fukushima nuclear reactor accident. Now, actually speaking, the casualties of these accidents are very, very low. In nuclear reactors, in general, when some nuclear explosion or the reactor accident takes place, the majority of the casualties happens due to the thermal burning. I mean, the heat radiation. Of course, some accidents may take place because of the high radiation exposure also. But now, let us see what how it is regulated. See, all the nuclear reactor generates high radioactivity. Of course, there is no doubt in that. Now, in India, we have an Atomic Energy Regulatory Board, which regulates and activates the nuclear energy program. And let us see quickly what are the elements of the safety regulation. One is the siting. That means if you want to set up a nuclear power plant, first of all, a very stringent element is the siting of that location, whether the site is proper or not. In siting, they look at many aspects. What is the seismicity? That means whether it is prone to earthquake or not. If it is prone to earthquake, and if you set up a nuclear plant there, and if some seismic activity takes place, then one day, one good morning, it may break away. So seismic, then the soil, type of soil, whether it is suitable for handling a very strong foundation for the nuclear reactor, the availability of the water, water is nearby or not, because you need to have cooling system, steam generator, a constant supply of water should be there. So all these elements will be, and what is the population density there, whether population density is as per norms, what are the impacts if something happens, all this proper assessment is carried out during the siting. Then you have an MOE of, that is Ministry of Environment and Forest clearance. Government of India will give that. So after a lot of public hearing, this clearance will be given. Then you have the construction and erection. Then comes commissioning, regular operation. But during construction also, it is not like simple construction. A lot of quality controls have to be ensured. International standards have to be mentioned, have to be ensured, and all the details have to be submitted to the regulatory board for the verification. And then regular operation at different stages of power. then thorough review at each stage. Then you have plant emergency, site emergency, and off-site emergency drills carried out very meticulously. Then there is environmental survey laboratories established at each nuclear, plant site. What they do is that, first of all, before the establishment of a nuclear facility, all the baseline data is supposed to be established, like what is the natural radioactivity level in drinking water, in soil, in the vegetation which is locally grown, in the air. All these elements are the baseline data are measured. Then subsequently, when the reactor goes into operation, periodically all the elements are to be like, suppose if you go to market, from the market they take samples, they process it, and then do the measurement for any increase in the level of radioactivity, either in the, for example, maybe poultry, maybe vegetables, maybe pulses, maybe tea, whatever things are available in the market, all those things will be brought and tested in this laboratory. Then quality of water, then the quality of air, continuous monitoring will be done. And then finally, the radioactive waste management. And these are all as per the international guidelines, which is implemented by the Atomic Energy Regulatory Board. And of course, subcritical reactor does not have so much of problems, but I missed one slide. Actually, I wanted to show a slide. Why do we want this nuclear energy? See, one reason I said is about the thorium utilization and the energy security for nearly 500 years. The second important aspect is that, see, you know that 60% we are using coal. Now, world over, a very serious issue is, a burning issue is coming up, which is called the global warming. And what is this global warming? Global warming is due to the emission of carbon dioxide. This is a greenhouse gas, that carbon dioxide which is emitted if you operate a thermal power plant. And in fact, I had a slide which I missed. See, I got that. See, around 30% of the carbon dioxide emission is the European statistics says that around 30% of the carbon dioxide emission is from the coal-based nuclear power, coal-based plants or the thermal plants, or the burning of the fossil fuels, etc. So now, if you allow this, see, we are not against any type of reactor system or the energy system, but only thing is that what is the advantage, what is the disadvantage, and how we can get away from the disadvantages if you have a better option like solar energy. Solar energy is coming up very, very vigorously. It is in India also. It is coming up. The percentage of solar energy is going up in a large scale. There is a separate program for the solar mission program is there by the government of India, not only in India but world over. That also has problems. Anyway, we will not go into the details of that. But this greenhouse effect, since nuclear fission is a clean energy, it does not at all give rise to greenhouse gas effect or the global warming effect, which is a very, very important things to be seen. And in summary, the energy potential of uranium is almost 1,000 times that of coal. So that means if 1 kilogram of uranium, if you compare with coal, it is almost around 1,000 times, 1,000 tons, you can say. 1 kilogram is equal to 1,000. Now the world nuclear energy share is 40%, whereas that of India is 2%. This already I have told that 22 nuclear power reactors are operated by NPCL, that is Nuclear Power Corporation of India Limited. This is generating around 6,780 megawatt. 7 units are under construction, expecting the completion very soon. And we have a 3-stage nuclear program for ensuring the energy security of our country. Third stage is focused on thorium utilization, which is expected to give an energy security to several hundreds of years. And ADSS is conceived by BAE, and several research studies are in progress, which is mainly focused on the thorium utilization and incineration of long-lived radioactive waste. And environmental impact of nuclear energy is negligible. So with this slide, I give a big thank to all of you for listening to me, and probably I think I have done justice to you, because I do not know, because as a student I try to come up to that level and try to convey what I want to say to you. I hope you have understood, and you could get a significant amount of information about a broad view of what nuclear energy is and what India is doing for the energy security. And as my friend Dr. Jayaprakash also told me that because you are young students, and as Professor Jairaj in the beginning mentioned about the opportunities, because in fact he made a very important statement which has a long impact. See, of course we study and we look for some job for earning for our livelihood, but now we can also create jobs. See, if you think in that direction, then one can, because all these scientific discoveries, see for example the web page, I am sitting here and speaking to you. This has been created just for a scientific data exchange at CERN. You know, we have a European Center for Nuclear Research at Geneva, Switzerland, where a lot of European countries are associating in various experiments. You might have heard about Higgs boson and all, which was discovered a couple of years back. So in the beginning of the CERN, since many countries are involved, they were not able to communicate properly. And for that communication only, this web was created, and you see how applicable it is, how widely it is used nowadays. So similarly, we can also create jobs for this. So that statement had a very long impact, and I think that you young students should develop an interest towards science, physics, chemistry, whatever stream you follow. You should develop an interest towards science, and it will play a long in the long run, and give a lot of satisfaction if you do some justice in the form of giving some contribution to the society as a whole. So we have in our department many opportunities. In fact, what I will do is that I will just list the opportunities, and I will share it to Dr. Jayaprakash, and he can communicate to you. But the main opportunity we have is the after post graduation, we have some training schools. For example, BARC is conducting it. We have training school at BARC, at our place, RRCAT, Indore, at Kalpakam, at NFC, Hyderabad. At these 4 places, we have training school where they take the bright students after post-graduation in science, especially physics, chemistry, metallurgy, but physics is more, the number of seats are more for physics candidates, and of course engineers. After completion of the post-graduation of engineering, either if you have a GATE score, through GATE score you can directly apply, or there is a entrance examination conducted at the national level, which I will share the website and information, so you will get that. So you apply that, which is called the orientation program in engineering sciences. So there will be that one, once you clear that examination, it's a multiple choice type of examination, then you have an interview. You once it is shortlisted, then you will have to face an interview, and after that interview, if your performance is very good, then you will be selected. So there is a rigorous process of selection is there. Then after the selection, 1 year you will be put under training, where you will be taught many techniques, for example, computational techniques, simulation techniques, theoretical modeling, then experimental facilities, introduction to many experimental facilities. So then after successful clearance of this thing, you will be given the post of a scientific officer. It's a gazetted post. And then once you get into that, then it is like I would say that it is like a sort of very good opportunity where you will get all the facilities, medical facilities for the entire family. Then LTC once in a year, you can go anywhere in India or hometown. They will give airfare, etc. And good educational facilities. We have our own central school, Atomic Energy Central School, where children will be grown up in a very good. So all many opportunities are there. So that is for postgraduate students. So for undergraduate students, like BSc and all, there is another opportunity called, they take it as category 1 trainees. That is, after BSc, you can apply for that. Again, there is they gave you scientific assistant post. The first one was scientific officer, the second one is the scientific assistant. You will be given the post of a scientific assistant after test and interview. Then 2 years training will be there. After 2 years training, you will be inducted into. There is also a very good opportunity, but later on you will be promoted to officers and all. And this is in our department. The Nuclear Power Corporation of India, in the nuclear sector, they have their own training school. So I will share the websites of all these things. I will WhatsApp to my friend Jaiprakash so that he can share to all of you, so that whenever opportunity comes, you can look for that. So with this, I wish you all the best, all the students, all the best. And once again, I thank Dr. Jaiprakash and other faculty members of the head of the Department of Physics, Tungabhadra Marthama College, for giving me this opportunity to share my little bit of knowledge about nuclear energy to you. Thank you one and all.
Thank you very much, sir. Thank you very much for the very informative talk. It's a wonderful, and it's clearly explains everything about the nuclear power, the generation, everything. The first thing that when we heard about in the nuclear power generation, the first thing that comes in our mind is like the hazards and the main problems associated with that. But you have clearly explained about the problems, and also how useful and how we can utilize the energy, this nuclear power as the coming energy source for our needs. Okay, students and participants, please, if you have any questions, you can either directly unmute and then ask to sir, or you can type the questions in the chat box so that we can ask one by one. So there is one question by Jitin Govind. Sir, what benefits does thorium-based nuclear program have over traditional uranium-based nuclear programs?
In fact, that is a very good question. And I have cleared in one of my slides that the uranium cycle has got a lot of long-lived radioactive waste. Okay, where thousands of years of half-life. I said about the minor actinides and other radioactive like curium, americium, etc., neptunium, etc. So their half-life is very high. So storage is a very difficult problem. So thorium cycle, the advantage with the thorium cycle is that it generates less amount of radioactive waste with high half-life. See, for example, in normally the low half-life radioactive waste, what we do is that we keep it for some time. See, for example, a liquid radioactive waste. If it is kept for nearly an hour, say for example, half a month or maybe few months, the radioactivity will decay to such a low value that it is comparable with the normal level in the water. So there is something called discharge limit. In that case, you can discharge into normal sewerage line, right? But suppose if the activity, the half-life is very high, you cannot discharge into normal sewerage line like that. So what you have to do is that you have to store it for hundreds of years, thousands of years. It becomes a very big issue, big problem. So therefore, world over, it is thought that if uranium-plutonium cycle, if you keep on continuing, then there will be some way of converting this high half-life radioactive waste to short-lived, so that you can manage it very easily. This is the main advantage. Okay.
Thank you, sir. Any other questions? Sir, I have one question. In the summary slide, you have mentioned that the nuclear energy is nuclear energy is a clean energy. By
Right.
mentioning that, what about the nuclear waste? Because if it is not even exhausting any other gases, but the main hazard is in that waste disposal problem, right?
Right. Actually, that is also a very important question, which I think I should address that. See, normally what is the three types of waste are generated? One is solid waste, one is liquid waste, and another is the gaseous waste. The gaseous waste which is generated, normally it is discharged. You might have seen that very high cooling tower, I mean the tower, etc., where the gases are exhausted at a very high level of elevation. It is not normally released at say 5 meter or 10 meter, maybe 30 meter, 40 meter, 50 meter height.
Yeah.
And the idea is that once you release that, then there is a process called dispersion. So these gases will disperse, and finally when it comes to the area where population is there, it will come down to a very detailed simulations are carried out for ensuring this thing, and it is discharged. Okay. I mean, there is another issue which is addressed, that suppose if at the release level, if the activity is high, then it will automatically block the release, right? So that it will not go into the public. There is a release limit for each thing. There is a release limit. That is about the gas. Then liquid, as I said, that the liquid, if it is a short-lived activity, then there is a process called delay and decay. If you delay, then it will decay. And once that it comes to the acceptable level, you can discharge it. But solid waste, the problem is the main problem is the solid waste. Solid waste, what is normally done, that you cannot leave it in a room or anywhere. So for that, actually that is another lecture. It is another 1 hour lecture, waste management. So there they mix this radioactive solid with what you call glass. Okay. And in a glass matrix, this will be, because glass, it is not reactive with anything, right? So in a glass matrix, that process is called vitrification. You vitrify the radioactive waste in a glass matrix and store it in deep repositories. That means at a designated place, you have to create deep trenches with concrete and with stainless steel lining, etc., where even for thousands of years, it will not have any damaging effect. So it is kept in deep repositories. So it will not have any impact to the environment outside. So, and then another thing is that there is no release of greenhouse gases like carbon dioxide and all. So environmental impact as such is negligible, except in the reason that if there is a nuclear accident which takes place, like that has happened in Chernobyl and all, if the reactor core burns out. Nowadays, there are many techniques, many redundant safety systems are there. If one fails, the other takes over. And I tell you one important thing I want to share, that most of the cases, the accidents takes place because of the human error, which we overlook. Safety systems are in place. I'll tell you one simple example.
Mhm.
A couple of years back, you might have heard that at Calcutta, one hospital, Amri, it is called Amri Hospital, one fire incident took place and where 100 people died.
Mhm.
Now, when they investigated, they found that for the detecting the fire alarms were placed there. And now these West Bengal, these people have the habit of smoking and all. Some operator means some staff, nurse or somebody, they in the room, they disable the fire detection system. They bypass the safety system and then they started smoking there. And from there it has reached, it is around 100 people died. So International Atomic Energy Agency has studied the nuclear accident happened across the world and they found that the major cause is due to human error. So therefore, systems are in place, but training is a very important. See, as I said, that's a 1 year training course is given in NPCL, etc. They impart training in each and every front, including the safety aspects, including the responsibility of each and every person, including the safety culture. It is given. So in that context, it is I would say that it is totally a clean energy, right?
Okay, sir. But still, we have that doubt in what it's not a. I understood what is meant by clean energy, but yesterday I have heard from the news that in 2011 Fukushima has that accident, and they have used some water to clean that reactor. And yesterday the news was like this: the country is planning to what allow the water to go into the sea, and many people are coming to against that, but they haven't taken the final decision what is that they have said. What about can you comment on this? I mean, there are
Exactly. Actually, see, nobody will throw, contaminated water into the normal water stream and all those things. Once it is decided to throw into the normal stream of water, the level has come down to a low value. Then only they will do that. See, I tell you one thing. See, it is a Kodankulam nuclear. First of all, Fukushima. We talk about Fukushima. Fukushima. Nobody died of this radiation exposure or because of the nuclear disaster. See, even Chernobyl, I tell you, it is because of the fire or it's a burning hazard. People have died. Okay. Now, once it is decided to discharge, that means the discharge limit has reached. Absolutely, there is no problem. But the problem is that the fear. Once you have a fear in your mind, see that Kodankulam nuclear reactor, when it was about to establish in 2001, 2009, etc., you might have heard that the fishermen were conducting a lot of strike there, telling that it is going to happen. See what fishermen understand about nuclear energy. Can you just imagine?
Mhm.
So unless you have, and I tell you, if you look at the statistics of fatality happening in our country, see each and in 3 minutes, one death is happening in every 3 minutes in the road accidents, right? So that is, you might have, you can imagine that, see 1 hour, how many deaths have taken place? Around
Yeah.
30 deaths have taken place, right?
Yeah.
Right. But then due to cancer, people are almost 6 to 7 lakhs of cancer deaths are taking place in our country per year. It's a very alarming. But if you
Yeah.
look at the death rate or the fatality rate due to nuclear accident, you can say that it is almost zero. So we have to understand the reality and the statistics. See, if you carry with fear, if you ride a scooter with fear, you will fall down. So you have to understand the physics behind that. The limits of this radiation exposure, the limits are set by International Atomic Energy Agency, International Commission of Radiological Protection, in such a way that it is the lowest, risk. Or if you compare the risk from various, actually there is a slide, because of the lack of time I could not show. Various industries like textile industry, cement industry, deep fishing, cigarette smoking, nuclear industry. There is a list of risk from all these industries. And if you look at that table, it is the least risk is from the nuclear energy. So that itself tells that. The only thing is that through this type of lectures, we can educate people. We have a public outreach program. Of course, we have a Department of Atomic Energy has a public outreach program where we go to various colleges, go to schools and exhibitions we conduct, and we tell about the reality, the science behind that, and people accept that. Right.
Yeah, thank you very much, sir. So your conclusion is like with a proper training and efficient management system, nuclear power become the most efficient way for generating the necessary energy to the country, right?
Of course.
Okay, thank you very much, sir. It's a very informative, wonderful, very good talk. Thank you very much. Any other questions from the participants? I think it is like the community from nuclear people like you have to conduct lectures to many colleges so that the students will be maybe more aware about such things. Because even though I don't know about, means I said earlier, like when I heard about nuclear power, the main thing that the first important thing that comes into my mind is the hazards and the problems related to that. We don't think about what is the means positive things coming from there. So it's very wonderful. Thank you. Very informative talk, sir.
Yeah, right. Thank you so much.
Okay, I hope there was no other questions. Students, please fill the feedback form to get your certificate. And there is one announcement, like we have, this is our final lecture in the Phytech series. So from the next week onwards, we will start distributing the certificate. Those who have filled the feedback form will get the certificate soon. We will also provide the Phytech series certificate for those who have attended all the talks. So don't worry about thing. If you missed the feedback form, and we have to cross match, and then we will let you know if you are you're able to get the certificate. Okay, thank you very much, and I invite Mr. Kishan Kumar sir to deliver vote of thanks.
Thank you, Shilimis. In this occasion, I am recollecting the memory about commissioning the Indian Neutrino Observatory also now. As Haridas sir said, the people do not have the sufficient knowledge about the projects. That's why the problems are coming from the part of the people. I would like to thank. I would like to deliver the vote of thanks for this program. So I am going to do that. First of all, I would like to thank Dr. M.K. Jairaj sir, the Honorable Vice Chancellor of Calicut University, for spending his valuable time for us. Thank you, Jairaj sir. Next, we have a very good, wonderful lecture of Dr. Haridas G. Nair from RRCAT Indore, who explained each and everything of nuclear programs of Indian nuclear programs, and the hazards and the opportunities of for students in these projects. I would like to thank Dr. Haridas G. Nair for delivering a wonderful lecture. Thank you, sir. Next, we have the Dr. Reina Thomas, Principal of Marthoma College, Chungatra, delivered the presidential address. I would like to thank Dr. Reina Thomas for constantly supporting us through the webinar series. Thank you, madam. Then our college bursar, Reverend Mathai Joseph Achan, was with us. He was constantly supporting us or encouraging us to conduct these lectures. So I would like to thank Reverend Mathai Joseph Achan. Thank you, Achan. Then the constant support and the physical supports are given by the IQSC of Marthoma College, Chungadara. I would like to thank Dr. Rajiv Thomas for constantly giving us the physical facilities for conducting this webinar series. Thank you, Raju sir. And here we can see the retired faculty members. Thomas K. George sir is here, and Susan Miss was there. And I would like to thank retired faculty members for constantly supporting us. Then some of the thank you, Thomas sir. Some of our faculty members are also participating in the webinar series. Sanoj sir and Reena Mary Abraham teacher was here. I would like to thank them also in this occasion. Then I would like to thank Dr. R. Jayaprakash, head of the Department of Physics, for constantly organizing the webinar. Throughout the webinar series, he is constantly organizing us to directing us to do this. So I would like to thank Dr. R. Jayaprakash in this occasion. Then I would like to thank Mr. Dinoj for giving us the technical support throughout the webinar series. Thank you, Mr. Dinoj. And finally, I would like to thank my colleague, Dr. Sheelu Abraham, for doing each and everything for conducting this webinar series. Thank you, Sheelu. And finally, our students and the participants of Phytech 2020 webinar series is the main, it gives the main success of the webinar series. So I would like to thank each and every one of the participants of webinar series Phytech 2020 organized by Department of Physics, Marthoma College, Chungatra. Thank you all. Thank you.
Thank you, Kishan sir. And I would like to thank everyone, each and everyone, for your presence, for the enthusiasm that you have shown towards the Phytech series. All the participants, thank you very much. And we will let you know if we have conducting any such seminars in the future. We'll inform you. And I would like to thank Hazar sir once again for this wonderful talk. Thank you very much, sir, for spending your time and energy. And I would like to thank all the supporting staffs, and especially Kishan sir is doing a major part of while organizing this seminars on the whole series. Jayaprakash sir is giving full support and always ask about the means what the progress in all these seminars and programs. Thank you very much, sir. Thank you, everyone, college management, principal ma'am, IQC, and our retired staff for the continuous support, and for everyone. So our Phytech 2020 series ends today. And we are ending with a wonderful lecture. Thank you very much. I hope to see you all soon in another webinar series. Thank you very much. Thank you, sir.
Thank you, sir.
So the meeting ends here. You can leave the chat room.